Please start, ma'am.
Okay, so good morning, one and all. Welcome to Amity University. This is the 19th webinar from Amity International Society for Natural Products, and we proudly welcome Professor Diwan S. Rawat from Department of Chemistry, University of Delhi. So, on behalf of our Honorable Founder President, Sir Dr. Ashok K. Chauhan, our Chancellor, Sir Dr. Atul Chauhan, our Vice Chancellor, Ma'am, Dr. Balwinder Shukla, Ma'am. I welcome one and all who have joined us from India and all over the world to this webinar titled Fun of Playing Around NMR Spectroscopy. We'll be also joined in the panel shortly by Group Captain Kapil Shukla, sir. He is Assistant Vice President for Amity Science, Technology and Innovation Foundation. We have Dr. Rajiv Sharma, sir, who is Scientific Advisor to Honorable Founder President, sir, and also he is ex-Secretary, sir, and DG for Amity International Alliances, Dr. Selvamurthy, sir, who is President for Amity Science, Technology and Innovation Foundation, Dr. Nutan Kaushik, ma'am, who is Director General for Amity Food and Agriculture Foundation, and also an important part for Amity International Society of Natural Products, and all the faculty members, the students, and all the scientists who have joined. Welcome once again. And we are very thankful to Professor Rawat sir, who despite of his very hectic schedule could take out time for us. And before I request sir to uh, deliver his webinar, I just want to go through his uh, resume. Sir has done his MSc from, he's a gold medalist in chemistry from Kumaon University, Nainital, 1993 batch. Has done his PhD from CDRI, Lucknow. Sir had been associated in scientist position at Panchil Organic Limited, Lupin Labs. He had been a postdoctoral fellow, NCI postdoctoral fellow at Indiana University, USA. From 2001 to 2, he was NIH postdoctoral fellow at Purdue University, USA. From 2002 to 3, he was at NIPER Mohali, and from 2003 to 10, he was associate professor at Department of Chemistry, and 2010 till date, he is a professor at Department of Chemistry, University of Delhi. He has published over 150 research papers in international journals of repute. Citations count to 4,700. H index of 43. He has 9 granted patents, and he was all over the newspaper for his drug got tested through US FDA for Alzheimer. He has supervised over 22 PhD students, and Sir is associate editor for Nature Scientific Reports, RSC Advances, Everyman Science. He is a visiting professor at Japan Advanced Institute of Science and Technology, Japan. Sir is a member for Project Advisory Committee of DST Women Scientist Scheme. He is a member for Project Advisory Committee of DST International Division and Inspire Scheme. He is a national GLP auditor. He has got many awards to his credit. To name a few, he's sectional president. He was sectional president of Indian Science Congress from 2019 to 20. CRSI Young Scientist Award 2007. He's a recipient of Young Scientist Award ISFB in 2010. He got Professor D.B. Chakravarti 60th Birth Anniversary Commemoration Award in 2007. VC's Pratik Chinha Samman from Kumaon University, Nainital in 2011, Golden Badge and Diploma from International Scientific Partnership Foundation, Russia in 2015, Professor R.C. Shah Memorial Lecture Award, Indian Science Congress in 2015, Professor S.P. Hiramat Memorial Award, Indian Council of Chemists 2016. Professor Rawat is a Fellow of Royal Society of Chemistry, FRSC and CChem London. Uh, in the from administration side, Sir is chairman, governing body. He was chairman and governing body at Shahid Rajguru College, University of Delhi from 2011 to 12, and Deen Dayal Upadhyay College from 2019 to 20. He was coordinator for MTech Department of Chemistry, University of Delhi from December 2010 to 16. He was the provost for Jubilee Hall, which is very famous, University of Delhi from May 2012 till date. He is OSD University Press and head Graphic Arts Center, University of Delhi. He is treasurer, governing body for Sir Arvindo College, University of Delhi, Swami Shraddhanand College, University of Delhi, Khalsa College, and Aditya Mahavidyalaya, University of Delhi, Treasurer, Delhi University Students Union from 2012 to 17. He was warden for Jubilee Hall from 2003 to 12. Chief Election Officer for DUSU Election, University of Delhi from 2014 to 2017. So with so many credentials, and sir is also associated with Amity for many years, we thank sir for his collaboration and also for his immense support. Always, he's always ready, and we warmly welcome you, sir, and we are eagerly waiting to listen to you, sir. So over to you, sir.
Thank you, Dr. Harsha, and thank you for your kind word of introduction and invitation. And I must thank for you. I mean, you have been taking so much of pain to organizing such a beautiful webinars. And I think these many webinars by a single person I have not seen. So committee must be proud of you. With this note, today I'm going to talk about NMR spectroscopy. When we talk about NMR spectroscopy, 1 hour lecture is nothing. It means in between I have to skip so many important things, but the talk what I have arranged, it is arranged for the master's PhD student and the faculty member who teach this course.
Yes.
And this is the most difficult as a teacher to deliver a talk when you don't have audience in front of you. Whenever we deliver a talk, you have audience in front, and you can see the reaction of the students or the faculty members, and you can change your way of presentation also. But in this mode, that option is not there. But I will try my level best to make this talk as interesting as I can. About 2 weeks back, I delivered one talk to Punjab University, Chandigarh, and that was uploaded in the YouTube. And I'm told that the recording will be given to me, and I will upload this talk also in the YouTube. And the content of the previous talk and this talk is almost different, so it is not same. When we talk about NMR spectroscopy, why NMR spectroscopy is so important, that can reflect with this slide. The importance of this technique can be realized by the fact that 8 scientists got Nobel Prize for the development of NMR spectroscopy. The first being Otto Stern in 1943 for physics. Again, 1944, it went to physics to Sridhar Ravi. Then chemistry in 1952, Felix Bloch and Edward Purcell. Then 1991 for HR high resolution NMR spectroscopy to Ernst. And in 2002, 3-dimensional structure of macromolecules was given to Woolrich. And 2003, it was for MRI development by Lautenberg and Mansfield. And this MRI was based on the principle that was discovered by Mr. Ravi way back in the 1940s. And when he suffered cancer, actually, and his cancer was detected by this MRI. And what he said, I saw myself in that machine. I never thought my work would come to this. So this is the beauty of the scientific inventions. And when we talk about NMR spectroscopy, actually, we always start with the discovery made by Bloch and Purcell. We don't talk about other people's contribution in this field. And in 1946, Bloch from Stanford and Purcell from MIT published 2 independent papers in physical reviews in the same journal. And the science of the paper by Bloch was half page, and Woodward Purcell paper size was 1 page. That half page and 1 page research paper led them to get the Nobel Prize. And the physical terminology, what they discussed, both of these people were different. Bloch said it is nuclear induction, and Purcell said it's a nuclear resonance spectroscopy. So NMR spectroscopy term was given by Purcell, and the FID term what we use, it is given by Bloch. Still, if you talk to the physicists about NMR, they don't talk about resonance, they talk about induction. Okay, and another beautiful story on the NMR is of Richard Ernst, who got a Nobel Prize in 1991. You know, his paper was rejected twice by Journal of Chemical Physics, for which he got a Nobel Prize in 1991. And he could finally publish this paper in a review of scientific instruments. And his first paper outlining the technology of application of Fourier transform spectroscopy to resonance, magnetic resonance, received very little attention at that time. So this is what the beauty of scientific discovery is. Sometimes you don't realize the importance. So there is no takers in the beginning, but he got the Nobel Prize at the end. So when we talk about the NMR spectroscopy, let me make one thing very clear before I move to next slide. When we talk about NMR spectroscopy, we talk about the magnetic property of a nucleus. Remember, we are not talking about magnetic property of any atom. We are talking about magnetic property of a nucleus. That nucleus can be of anything. It can be a proton, it can be a 13C, it can be a nitrogen 15, fluorine 19, then 31 phosphorus, anything. Okay, so we are talking about the magnetic property of a nucleus. So when we talk about the nucleus, nucleus consists of neutron and proton, that we all know, and nucleus have the intrinsic quantum property of spin. And overall spin of a nucleus is determined by a spin quantum number called I. If both protons and neutrons in a given nucleus are even or same, then the spin quantum number is 0. So any nuclei, atomic nuclei that have spin quantum number 0 will be NMR inactive. So let's try to understand this by a simple example. Here you have a hydrogen, that's what we call sometimes proton, and this is the nucleus. Okay, nucleus of hydrogen consists of one proton only, and it has overall nuclear spin of half. Okay, now if you consider the nucleus of 12 carbon, it has 6 proton and 6 neutron, and its overall spin is 0. Any atomic nuclei that has net spin quantum number more than 0 is NMR active. So it means from the periodic table, all those elements are NMR active which has net spin quantum number more than 0. So similarly, carbon 13, in carbon 13 you have 6 proton and 7 neutron, and its spin quantum number is half, so it is NMR active. So nucleus is positively charged, we know that. It has a property of spin. So any spinning particle that has a charge, right, and it has a spin, will behave like a bar magnet, right? So when we say bar magnet, it means it will have a magnetic field. Okay, any magnet will have a magnetic field. How much is the magnetic field? That is the magnitude. What is the direction of that magnetic field? How you know that? That you can determine by a vector called magnetic moment. Okay, so each of the atomic nuclei has a magnetic moment if it is NMR active. Okay, Another thing is, when we talk about this magnetic moment, let me show you how it looks like. Okay, in absence of any applied magnetic field, let us suppose there is no applied magnetic field in the system, how the magnetic moment of a proton or a hydrogen looks like. It looks like this. What does it mean? It means the magnetic moment is directed randomly. It can go upside, it can go to this side, and this. It's randomly oriented. But if you place this in the applied magnetic field, the proton's magnetic moment adopts two orientations. One, now this is your magnetic moment in absence of the applied magnet. Now you apply a magnetic field like this to this direction. So what happened? This magnetic moment now adopts two orientations. What is that? It's like this. One that goes parallel to the applied magnetic field. This is the direction of the applied magnetic field. So this is parallel to applied magnetic. There can be another option, another way, which opposes the applied magnetic. It means under the influence of applied magnetic field, the magnetic moment of hydrogen nuclei adopts two conformations or orientations. One goes parallel to the applied magnetic field, another opposes the applied magnetic field. So how it looks like? So this is the applied magnetic field now. Okay, this is when the field, applied magnetic field is 0. Okay, now if you increase the field strength to this direction, what happens? This, it gets two spin states now. One spin state we call alpha spin state, the lower in energy. Another is the higher in energy, we call it beta spin state. Okay, this is called a beta spin state. So what happens if you increase the field strength from 300 to 600 megahertz? What happens? The energy gap from alpha spin state and beta spin state increases. Okay, so if this spin state increases, the resolution increases. What does it mean actually? It means that the population between alpha spin state and beta spin state is too small, population difference. Okay, the population difference is so small, and that small population difference is required for the NMR spectroscopy. From where this comes, spectroscopy, I talked to you about nuclear, then I talked about magnetic, and third one is resonance. In chemistry, resonance means the movement of the bonds, right? The pi electron and the pi bonds. But in case of NMR spectroscopy, what we call here, the alpha spin state is in resonance with beta spin state. It goes up and comes up, goes up, comes up. So it means it is in resonance. So when we talk about NMR spectroscopy, there are two things which are very, very important. One is shielding, deshielding. Another one is equivalent and non-equivalent. Now you can think here, some of the people who are the beginner can think in this way. We are talking here about the nucleus of a proton or a hydrogen, right? Why should hydrogen give you different signals in NMR spectrum, right? But we are talking about the magnetic property of the nucleus of a hydrogen atom. Hydrogen is same for everywhere. So why should it give you the different signals in NMR spectrum? And that different signal in the NMR spectrum, what we call it a chemical shield. Remember, we are not talking here about hydrogen atom. We are talking about hydrogen which is covalently bonded with a carbon or any other atom. When it is bonded with something, there is a bonding pair electron. Okay, and that bonding pair electron affects the resonance frequency of that particular nuclei what we talk about. So NMR spectra is a plot of applied radio frequency versus absorption. The applied frequency increases from left to right side. So this left side, what we call as a deshielded region, high delta value, and the right side, what we call the shielded region, the smaller delta value. variation of nuclear magnetic resonance frequencies. Okay, so which proton will absorb at which frequency? It depends on the electron density of the sigma bond by which it is attached with the carbon. And that is why it is called a chemical shift. So the sigma bond means the chemical bond. So this is why it is called chemical shift. And it is expressed in ppm, which is independent of the spectrophotometer's frequency. Now, when we talk about the shielding, deshielding, classical textbooks, this is the figure. What it says, this is your nucleus, which is possibly charged, and this nucleus is surrounded by electrons. Okay, electrons are moving around this nucleus, and this is your applied magnetic field. Okay, so under the influence of the applied magnetic field, the circulating electron of a sigma bond induced a secondary magnetic field, what we call an induced magnetic field. Okay, when this induced magnetic field is parallel to applied magnetic field, that region is called deshielded region. If the induced magnetic field opposes the applied magnetic field, that region called shielded region. So it means in this system, this area is the deshielded one, and this area is the shielded one. So the origin of NMR spectra is based on this applied magnetic field versus induced magnetic field direction. If they go parallel, this is called deshielding. If the induced magnetic field comes in opposition to applied magnetic field like this, it is called shielding. That is a beautiful explanation in the text. But the problem is when you go to the classroom and you want to teach to the students methyl chloride versus methyl bromide. Okay, this is deshielded in comparison to this. How to explain this in terms of this induced magnetic field versus applied magnetic? Is it difficult? For that, the simplest thing can be take the example of electron density or electronegativity of Cl versus Br. Let me show it graphically. Let us suppose you have a molecule here, this one. This is your carbon, this is your hydrogen, this is the sigma bond. Okay, and carbon is attached with a oxide. In one case, this X is electron donating, it is donating the electron. When it donates the electron, what happens? The electron density around this increases. Yeah, excuse me, just a minute. Namaskar, sir. Hello. हाँ सर मैं भेज रहा हूँ excuse me just a minute please. Sorry, I had an appointment in hospital actually. Let me just. Yeah, sorry. So in this case, what happened? The electron density increases here. So when electron density increases, what will happen? It will shield the nucleus now. Okay, and this shielding causes upfield shift. Upfield means low delta. In another case, you have X is electron withdrawing. When it withdraws the electron density around this nucleus decreases. So it is called deshielding high delta. So it means what are the factors that affects the chemical shift? One is electronegativity. Another one is the S character, that is hybridization effect, magnetic anisotropy, steric hindrance, hydrogen bonding. I will explain one by one all of these. Let me give you first example of electronegativity, how that affects. So you have a methyl group here, okay, and the methyl group is attached with fluorine, OH, Cl, Br, and I. And this is the electronegativity chart. 4, 3.5, 3.1, 2. So it goes decreasing like that, all of you. Now look at the chemical shift values. It perfectly matches with the electronegativity order of these atoms. What is happening here? When you have a fluorine, it's an electron withdrawing group. It pushes the electron to this side. The electron density around this hydrogen decreases. It means deshielding, downfield, high delta. So this is what the order is. That perfectly matches with chloroform, bromoform, and iodoform. You have 3, 3, 3, Cl, Br, and I. Electronegativity goes down. Same is the chemical shift. Oxygen, nitrogen, sulfur, same is the order. And in C13, I will not talk about it, but look at this. When you have a methyl group attached with fluorine, it is 75. But when it is with iodine, it's minus 20. This is very, very important. So I will not talk this tomorrow today. Now, if you look at this structure here, chloromethoxyacetonitrate. Okay, CN is more electronegative than Cl. So what I taught you, more electronegativity means more deshielding, downfield, high delta value. These are the two chemical shift values. So based on this definition, what I taught you, this should be more deshielded than this one. But whether this is correct or not, I will come and discuss this one a little bit later. I will leave it like that. Now, if you look at the nitro, NH2, NSCO, Ne, this CS2 right here, this is the chemical shift order. Okay, nitro CS2 is most downfield. Look at this structure here. You have CHNO2, you have CH2OH. Oxygen is more electronegative than nitrogen actually. Okay, but when it is nitro, it is the same or what? Look at the NMR spectrum. This is the peak for this CS right here. So NO2 attached with CS is more downfield than CS2 attached with oxygen. This is because this is how the resonating structure is. Because the nitrogen bears a positive charge here that causes downfield shift of this proton. And similarly, if you have a CS2OH here versus NO2, NO2 causes more downfield shift in comparison to OH. In NMR, actually, in chemistry, we always say that methyl group is the electron donating group, right? We all know that. It is an electron donating group. If that is correct, what happens? This methyl, there are 3 methyls. So electron density around this must be the maximum one, followed by this, followed by this. So electron density maximum means what? Shielding, upfield, low delta value. It is not. Why this so? This is because the carbon is slightly more electronegative than hydrogen. So that takes the precedency. Another beautiful concept is when the S character of carbon atom increases, the electronic cloud is held more closer to the carbon. It means what? The electron cloud will decrease in the hydrogen, deshielding downfield. So this should be the order: sp, sp2, sp3. It's not. This is the order. So what it tells there are some other factors which can affect the chemical shift values, and one of the factor what we call is anisotropic effect. In case of the pi system, let's take the example of your benzene ring here. So benzene is a flat molecule. If you apply a magnetic field from here, so induced magnetic field goes like this, okay, like these arrows. So any hydrogen that comes to this side is a deshielded. But if something comes over here, that will be shielded. So what will come in, on the top of the benzene? There is nothing, right? So all of the protons attached with the benzene ring are deshielded. But if you look at a paracyclophane, something like this hydrogen comes on the top of this benzene ring. Okay, that's a shielded region. So look at the chemical shift value, 4.17. Aromatic proton never comes below 6.5. This is the unique feature. This is why I have given. Now this is what I talked to you. although CN is more electronegative, but this is more dishielded. Why? Because of C triple bond C anisotropy. And because of this C triple bond C anisotropy, this methyl group is deshielded in comparison to this. Not only that, cyclopropane affects the chemical shift. Cyclopropane, we generally don't talk about cyclopropane anisotropy in the class, but we should. If you look at the this Nord-Bornean system, this hydrogen 3.99 ppm, when this is attached with, fused with cyclopropane ring, it causes dramatic effect on the chemical shift of value of this proton. Similarly, look at it here. You have a dimethyl group, you have a cyclopropane. Look at the chemical shift value change. Same thing, cyclohexene versus cyclopropane fused cyclohexene. So cyclopropane anisotropy affects chemical shift value drastically. Then you have a cyclohexane system. We all know that. You know, axial is the shielded cone, and this comes in the deshielded cone. And I will explain that as temperature dependent. Let us suppose you have cyclohexane DTN molecule. Excuse me. So if you look at this is cyclohexane D6, all of these are deuterated. Cyclohexane, we know it is a chair form. It goes like this. Okay, axial becomes equatorial, equatorial becomes axial. So at minus 59 degrees centigrade, you get a broad plate. But if you drop it to minus 89, so what happens? The ring flipping stops or slows down. So you see both of axial and equatorial proton can be separated. In case of this DMF kind of dimethyl acetamide, when we talk about acetamide, we have a double bond character here, actually, 1.5 bond order. So there is no free rotation. So one of the methyl is NT2 oxygen, and there is SYNAP2 oxygen. If you hit it, it's a single bond order. So you have a free rotation. So this will become same. Experimentally, that was good. At 38 degrees centigrade, you have 3 methyl groups here. 1, 2, 3. 53 degrees centigrade, this get broader. 84 degrees centigrade, both of these methyl merge gives you one single because of this structure. Steric hindrance affects the chemical shift. So if you look at it, compare this versus this, you have a hydrogen versus hydrogen, hydrogen methyl. So whenever you have steric hindrance causes dispersion, and dispersion leads to deshielding, downfield, high delta value. You can see all of these protons because of that. Look at it, naphthalene case, tertiary butyl group, 0.8 ppm difference. And in case of halogen substitute, if you have this H is halogen, fluorine, chlorine, bromine, and iodine, depending on the size, the deshielding takes place. In case of the cyclic system, if you have heteroatom substrate system, you have OCS2, OCS3, 3.5 to 4 ppm. But if you have a 3-membered oxygen shielding, because of the ring strain, it affects the chemical shift so drastically so that it is upfield. But in case of the 5-membered ring and 6-membered ring, it comes at usual position. Chemical shift of aliphatic amine and aromatic amine can be differentiated by NMR. How you do that? Look at it. This is aliphatic amine, comes less than 2 ppm. Aromatic amine 3.9 ppm. Generally, aliphatic and cyclic MS comes 0.5 to 3 ppm. Aromatic amine 3 to 5. Amide, phenol, and indole 5 to 8.5. This is how you can differentiate. And in case of alcohols and phenols, alcohols comes up to 4 ppm, phenols above 4 ppm. If you look at it here, this is intramolecular hydrogen bonding, much stronger than intramolecular hydrogen bonding. So this is 6, this is around 11 ppm. And this is about aliphatic alcohol, this is about 4. And keto-enol tautomerism, highly deshielded protein. Another important aspect in NMR spectroscopy is the equivalent and non-equivalent. This is the crux of NMR spectroscopy. So if you understand the concept of equivalent and non-equivalent proton, you can be master of NMR spectroscopy, and for that you need 10+2 chemistry only. Let me explain how. Homotopicity. If you have this alkene right here, okay, and substitute one of the hydrogen by D, you can get this or can get this. If you want to name these two compounds, what will be the name nomenclature? Nomenclature of both of these compounds. What does it mean? It means both of these hydrotropic protons are hydrotropic. Hydrotropic protons are equivalent protons. Now look at molecule ethane. Red and blue H substituted by D. You do that. What happens? If you want to nomenclature these two compounds, same nomenclature. So it means what? These are homotropic protons. Homotopicity can be studied by taking the example of axis of symmetry. If you look at this trans 1,2-dimethyl cyclohexane, and if you rotate this molecule with these two, with this axis on 180 degree, you get this. So if you can't differentiate these two molecules, it means what? It means both of these methyl and these hydrogens are homotropic. Homotropic means equivalent. Equivalent means same chemical shape. Now, if you want to look at topicity of this CH2 or this CH2, do the same thing. What happens here? They don't change the positions, but this and this are not homotropic because one is towards this methyl, another is anti to this methyl. So CH2 here is distereotropic. Now, if you look at cis 1,2-dimethyl cyclohexane, if you rotate it by 180 degrees, this is what you get. And now, when you rotate it, now you can see there is a difference. These methyls were up to the plane. When you rotate it, it goes to about down the plane. By eyeball, you can see there is a change in the structure. What does it mean? It means these two methyl groups are not homotropic. When not homotropic means what? They will give you different signal. Similarly, it has C3 axis of symmetry, so all the methyl groups are similar. So homotropic groups are not equivalent. And if you take the example of enantiotopicity, now take the example of N-butane. And these two methyl groups substitute by D. This is substituted by D, this is substituted by D. What it becomes? This becomes a chiral center, and this becomes a chiral center. Okay, so these protons are called enantiotropic. Remember, enantiotropic protons are chemically equivalent protons. Okay, for NMR signals, you need non-equivalent. So these are equivalent protons. And if you record the NMR spectrum of this compound, it will give you one signal only, cannot resolve. But this is the racemic mixture. Let us suppose you have a racemic mixture here. Okay, you have a chiral center. 50% of R, 50% of S. You record the NMR spectrum, it will give you only one signal. But if you add some chiral solvating agent, which has a chiral center here, what happens? When this goes in a solution, it forms a complex, right? It has a one chiral center, this has one chiral center. So this whole has one chiral center. Similarly here. So it means this proton behaves like a diisotropic proton. And diisotropic protons are non-equivalent protons. So in chiral medium, you can resolve the proton signal of a racemic mixture. Generally, we record NMR spectra in deuterated solvent, achiral medium. So in achiral medium, enantiotropic protons will give you one signal like this HA and HB. But if you add a chiral NMR solvent to this, what happens? You have this molecule which has an enantiotropic protons here. Now you have a solvent which is a chiral center. So this whole system now has one chiral center. If you substitute this by X, this also become a chiral center. So it means how many chiral center? 1 and 1, 2. So 2 chiral center means what? Diastereoisotope. So these two will be diastereoisotope. So it means non-equivalent. This and this will couple to each other. When they couple to each other means two doublers. So you can see two doublers here. Similarly, diastereotopicity. So if you substitute one of these two hydrogens by D like this, and if you see both of these molecules, if you want to write the nomenclature of these compounds, it will be a different nomenclature. So it means what? These two hydrogens are diastereotopic, so it will be non-equivalent. Now look at this molecule here. It is a chiral molecule, but it has a C2 excess of symmetry passing through this CH2. So whether these CH2 are equivalent or not, when the C2 excess passes through CH2 of which you want to see the diastereotopicity, it means these CH2 will be homotropic. Okay, so how many signals in NMR it should show now? 1, 2, 3, and 4. Look at the NMR. 1, 2, 3, 4. See, okay. Now look at this. This is glycerol, okay, and it does not have a chiral center here. So if you substitute one of the hydrogen by X, you get this. Now this is a chiral center. This is also chiral center. Okay, now it becomes a chiral center. It means these two hydrogens are chemically non-equivalent, and because C2 is not passing through this. So non-equivalent means this will couple to each other. You have another carbon here, hydrogen here, which will couple. How the NMR looks like? The NMR looks like this. One of the proton is this one. Another proton is this one. Look at the citric acid. Same thing. Plane of symmetry is there, a chiral, but C2 symmetry is not passing through these CH2s. So if you substitute HA, by X, becomes a chiral center. So it will be non-equivalent. And to that, you can draw Newman projection. You can see both HA and HB environment. It is totally different. If you look at the NMR spectrum, both of these hydrogens couple to each other, it gives you a double. Okay? So if you want to see the topicity, you should, in NMR spectroscopy, we see three kind of protons. Excuse me. We deal with CS3, we deal with CS2, we deal with CS. That's it. But yet we make a mistake when you are asked how many signals or non-equivalent protons are there. So whenever you are asked that question, please separate each kind of protons first and look them independently. Let me show you how. You have two methyl groups here. Let's see they are same or different. This methyl group is attached with CS2O. This methyl is attached with CS2CH. So different. So this is 1, this is 2. Look at now CH. How many CH? You have CH here, you have CH here. So this CH is aliphatic. So you have 2 count here. This becomes 3rd. Then you have this hydrogen aromatic, this hydrogen aromatic. So these are ortho to this group. Same. So 4. These are ortho to this MR. Same. So 4, 5. Now look at the CH2 group. CH2 group is typical in this case because you have a chiral center here. So if you substitute this one hydrogen by X, what happens? This is a chiral center, this also become a chiral center. It means these CH2s are diastereotopic. So 6, 7. Similarly, this one becomes diastereotopic. 8, 9. What about this NH2? Most of the time you make a mistake. You denote this as 1. It's not. Look at it. Why that? Because you have a lone pair electron here. So it will be on resonance, as in case of the DMF. So one will be syn to oxygen, another will be trans to oxygen. This is what the example is. Okay, so this compound has 11 non-equivalent protons. Isopropyl group, it's very, very important. Look at this. In textbooks, most of the time what it says, the methylene group next to chiral center is diastereotopic. No. The diastereotopicity can go up to 7 bonds in a chiral system. Okay, it is a diastereotopic group, not the hydrogens. Most of the time, if you look at the literature, these two methyl groups will be denoted as a doublet. It looks like this. If you expand this region only, see there, how many peaks there? 4. It means 2 doublers because these two methyl groups are non-equivalent. Substitution test chiral center. Okay, so remember that. I will leave this because I'm getting late. Okay, this is the summary of topicity. This is the example of enantiotopicity. There is a chiral center, so this becomes the diisotopic. This is the example of homotopicity. Now you have a chiral center here. So if you want to substitute one of the hydrogen, so these are diisotopic. A chiral system, but C2 axis is passing through the CS2. These are homotopic. A chiral system, but the C2 axis is not passing through this. These are diisotopic. Another important concept in NMR is magnetic non-equivalence, which is not explained very well. I will try to explain this with the example of para-nitrotoluene. If you look at these HA, I will call it HA, HA dash, HB, HB dash. Okay. Now, what do you do one thing? HA or HA dash, substitute by Br. So this is what you get. Now, if you want to give the nomenclature to these compounds, they have the same nomenclature. Means what? HA and HA dash are chemically equivalent. Now do the same test, HA and HB, substitute one by Br. You get this compound, you get this compound. If you want to nomenclature these two compounds, these are different compounds. It means what? It means the relationship of this HA with this HB is 1:2, right? This is ortho, but this HA has a different relationship with HB. So it means what? It means they are chemically equivalent, but magnetically non-equivalent. When we say magnetically non-equivalent, it means it's a coupling non-equivalent. Look at this spectra right here. When this X is equal to S or SO2, anybody ask you what will be the multiplicity of this? You have a CS2 here. So neighboring proton 2, you add 1, that will be a 3-line pattern, we call it triplet. This is what it should be. And the literature is full of this mistake. When you have sulfur and SO2, it is always mentioned as a triplet. But in 2011, it is confirmed that if you have X is equal to SO2, multiplicity of this is not a triplet, but a multiplet. Why this so? This is because of magnetic anisotropy. If you draw the Newman projection formula, you can see there will be magnetic anisotropy in this case. There is one question what we asked to the students. What we asked, how many signals following compound will show you NMR? Somewhere it is asked, how many non-equivalent protons present in the following compound? Out of these two questions, which question is correct? Let me give you an example here. You have 1, 2, 3. So 1, 2 dichloropropane. Okay, and you have a chiral center here. So if you substitute one of the hydrogen by X, this become a chiral center. It means these are diisotopic. So diisotopic means non-equivalent. 1, 2, 3, 4. How many non-equivalent? 4 non-equivalent. How many signals? 1, 2, 3, 4. So doesn't matter. If you ask how many non-equivalent protons and how many signals the following compound will show, both have same meaning, at least in this case. Let's move next slide. If you look at this compound here, it has 17 non-equivalent protons now. Count the number of signals. Can you count 17 non-signals here? Answer is no. You may be able to count 8 or 9 signals at the max. So when we ask this question, how many signals the following compound will show you in NMR, is a wrong question. It all depends with the complexity of the molecule, whether the spectra is of first order or a second order. So it is always nice to ask the question, how many non-equivalent protons are there in the following compound. Coupling, I will not go too much to it, but I will explain few things. Homotopic protons we talked about are equivalent, so they don't couple each other. Enantiotopic protons are also chemical shift equivalent, they don't couple. Diisotopic protons are non-equivalent, they couple each other. So when they couple to each other, I will not go to this tree diagram also, I'll skip this. I guess, okay, let me just explain this. So let us suppose you have HA, you don't have a neighboring proton there. So how the signal of HA looks like? One line. But if you have HB, which is magnetic, so net magnetic field experienced by HA is net magnetic moment of HA plus magnetic moment of HB parallel or minus. Okay, but it experiences both. It means HA resonances twice, one plus with HB, another minus HB. So it gives you two-line pattern. This is what we call a doublet. Similar is for triplet and quartet also. In case of the coupling constant, one thing we always teach to the student, that is a Karplus equation, diagonal. Okay, cis trans isomerism and all that. But we don't teach few other things to the student. As a result, they always make a mistake. I will give you the example here, fluoroiodoethane. So if the coupling constant of this CS2 is 8 Hertz, look at the literature. Most of the time, this coupling constant is also recorded as 8 Hertz. Because what they feel, if the dihedral angle is fixed here, same thing here, so it should be same. It's not. The J effect is affected by bond length, valence bond angle, and electronegativity. So if you look at this X here, I, Br, Cl, and F, this is how the coupling constant varies. So don't make that mistake. Another one is beautiful question what you are asked, how you differentiate cis and trans isomers by NMR. Answer is straightforward. More coupling constant for trans than cis isomer. Your answer is wrong because your answer was based on the assumption that cis trans isomerism is exhibited by alkenes only. What about the cyclic system? Okay, but question is still there. We have a cis and trans still being here. How you differentiate it? Again, people will answer. Trans will have a more coupling constant. Look at it here. Do the substitution test. See, these hydrogens are same or different. These hydrogens are same, homotrope. They will not couple to each other. In this case here, you have cis, this one, cis coupling constant is 6 to 12 Hertz, trans coupling constant 2 to 9 Hertz. So try to understand what question is being asked. So this looks like the, how the NMR looks like of these two. It will show you a doublets here, cis and trans. But in this case, you have this hydrogen flanked by this phenyl and this phenyl. So it means it is deshielded, downfield, high delta value in comparison to cis. And this is how it looks like. Now, if you go to this, what it says, if you have a two doublets like this, okay, if these two doublets are far away, you can see them 1:1 intensity ratio. When these doublets comes closer, the intensity of inner peak increases and outer peak decreases. Now you can think a situation where they come closer in such a way that the intensity of these four line peaks becomes 1:3:3:1. Okay, this is last and this is the in between. It's not same. But in case of the quarter, all these three values are same. So this is how you can differentiate cis and the quarter. I will skip this calculation. I will skip this also, but I will go to structure test, maybe a few more slides, maybe 10 minutes more. The importance of the spectroscopic technique is at the end of the day, you should be able to determine the structure of the compound. In most of the cases, what we do, we give you the molecular formula of the compound and spectral data. And that problem I would always consider is the easiest one because any molecular formula, whatever you are given, will have n number of isomeric structures. And then number of isomeric structure can be compared with your given data, and by mix match you can arrive with the answer of your question. Now think about it. If you are not given the molecular formula, let us suppose you have a natural product, unknown compound. You have IR, you have NMR, you have 13C, you have mass spectrum, no molecular formula. You need to determine the molecular. I will discuss one such problem for you. Now let us suppose you have a mass spectrum, and what this mass spectrum tells you, you have a molecular rate at 1, 1, 1, 2, 3, excuse me, 123. What it tells you? It tells you you have odd number of nitrogen. Remember, in mass spectrum, if you have EI technique and you have an odd number of nitrogen, your molecular weight always be odd. Okay, because this is what we call a nitrogen rule. Nitrogen, why this so? Because nitrogen is an element which is odd valency, even molecular. This compound does not have a Br, Cl, and sulfur. Why? Because if you have a Br has two isotopes, Cl has two isotopes, sulfur has two isotopes with different natural abundance. So you have only odd number of nitrogen. If you look at your IR data, you have 651 centimeter inverse strong absorption. What it says a presence of a CO group which is in conjugation, because acetone P comes at 1715 centimeter inverse. Now, if you look at the proton NMR here, this is the proton NMR. So this is the aliphatic region, this is the aromatic region, and this portion is the expansion of this region. What it tells you. Now, if you compare this with your C13, these are two positive peaks here, depth. Okay, if you have a positive peak, these positive peak can be CH or CS3. Now, if you look at this side, in the next depth, this peak disappears, and these are CS3. These are the positive peaks here. It means you have CH. You don't have a CH2 because you don't have a negative peak here. This peak has merged one quaternary carbon right here, another quaternary carbon here. So based on that, what we confirm that your system is aromatic system. Okay. So what we concluded? We concluded odd number of nitrogen, presence of CO group, presence of two CH3 groups, presence of 3 CH, and two quaternary carbons, 1 and 2. This is what the analysis based on this aspect. So the first thing is divide your molecular formula by 13. Whatever integral value comes, that will be the number of carbon atom present, and number of hydrogen will be number of carbon plus remainder, if any. So it means you have a 9 here, the molecular formula becomes C9H15 if your compound contains only carbon and hydrogen. Since we already have explained that it contains one oxygen and one nitrogen, so now what you do, you add oxygen and nitrogen to it and remove CH2 and CH4, because CH2 is 14, CH4 is 16 weight of oxygen. So the molecular formula becomes C7H9NO. When you calculate the double bond equivalence, it comes 4. So what we discussed? We discussed presence of odd number of nitrogen, presence of CO, 2 CH3 group, 3 CH aromatic, 2 quaternary carbons, including 1 carbon molecular formula. It means what? This. You can simplify it. You have CO group and you have a CH3. So you have CO CH3 group. You have a nitrogen and you have a CH3. NCH3, 3 aromatic, and 1 quaternary. Hook up to these, all these. This is the partial structure of your compound. If you move this, this is what the structure is. Now, somebody can ask, why not this is at this position? Now, look at, draw the resonance structure of this. This moves like this, comes here, positive charge here, this goes here, positive charge here. So, how many hydrogens are deshielded? 1 and 2. So, 2 deshielded means 2 signals should be close by in the deshielded region. Look at it. If you put your acetyl group over here, you will have only 1 deshielded proton. It means the order should have been reversed. So this is what the structure is. So this is the mass spectrum. So let me explain 2 or 3 net examination questions for you. This is the spectra. So whenever these kind of questions are asked you, because you are given the 4 options here, this is the easiest one, mix match, okay, rule out. So if you look at all these 3 structures, what is common? Common is all have same substituents. So don't look to these substituents here now, because they will not help you to assign your structure. But your substitution pattern is different in the aromatic system. That will help. So let us suppose, look at whether this system is there or not. Draw the structure. So what happens? This hydrogen is ortho to this hydrogen. So it is ortho coupling, 8 Hertz. This hydrogen is meta to this, meta coupling, 1.5 Hertz. Okay. So this should show you double doublet of 8 Hertz and 1.5. Similarly, this is ortho coupling and this is meta. So you should have 2 signals in the aromatic region, 2 doublets with this coupling constant. Do you have that? You have 1. That's it. You have only 1. So it means this structure and this structure is not there. Now, if you have this structure, if you have a meta coupling, 1, 2, 3, 3 doublets, what is the coupling constant? 1.5 Hertz. No, you have 8 Hertz. So this is all not there. So what is the answer then? Answer is this. Okay, this is how you go. The next one is this problem here. If you look at it, in this case also you have paradise, ortho and meta. Look at the NMR spectrum. In the NMR spectrum, you have 2 protons, 8 Hertz, 2 proton, 8 Hertz. 2 proton, 8 Hertz each in aromatic system can come only when you have para-disubstrate system. It means these structures cannot be correct. Out of these 2, 1 is correct. Now, if you look at this, remember the DMF case. If this is the structure, these 2 should show you 2 singlets. It's not showing you singlet of 6 protons. So what is the structure? Structure is this one. That's it. Now, the last one. Look at this now. In this case, you have trans, cis, cis. What is the coupling constant? 16 Hertz. So both cis structures are gone. Okay. Now you have this structure trans and this structure trans. You have OCS2 here, right? So look at 4.10 OCS2. You don't have OCS2 here. What is the structure? You can, you can solve these problems within a minute's time, but you need to be very, very mathematical with that. With this, I think I am done with this lecture. And as I said before, during this lockdown period, I have developed YouTube lectures to help out the students and the faculty members. And these are the 4 YouTube lectures I have already uploaded. One was in mass spectrometry, and another 2 are in this problem solution based on the spectroscopic methods. And third one is the NMR spectroscopy, but in that case I have covered many other examples. This lecture will be different than the previous one. And in the net examination, actually, only 17% students attempted the spectroscopy questions, and 3%. Yeah, I'm done. 3% were correct. So that indicates that the topic is not taught well, and I advise you to just visit these YouTube lectures, subscribe it, because I will be uploading in future also, and you will enjoy reading it. With this, let me just show you one beautiful slide, what I always show to the people who are my ancestors in my academic field. I did my PhD with Dr. D.S. Bhapani from CDRI Lucknow. Dr. Bhapani did PhD with Derek Barton, Nobel laureate from Imperial College London. He did PhD with Helborn with Hunt with Wilkinson, and I could go up to down to 1751. It's a Benjet Funnel from Uppsala University. Did a postdoc with Richard Gibbs from Purdue University. Gibbs did PhD with Okamura Kurtz with Woodward, the Nobel laureate. Woodward
Yes,
did with
sir.
Norris with Ramsden, then Fitting, Owner, the urea fame, Gamlin. Look at it. The the beginning person is one for both sides of the lineage. Another one is I did a postdoc
Wow.
with Jeff from Indiana University, and I could trace his lineage up to 1637. With this, let me just
Wow.
show you this is what we work actually. We work on medicinal chemistry and nanocatalysis, and this is our publication record. Anybody want to see can visit our website. And thank you very much for your patience hearing. As I said in the beginning, it's very, very difficult to deliver a talk in this mode because you don't have anybody
Yes.
in front, so we don't know how it is going. So I hope I was able to convey the
Yeah.
message to the audience. Thank you very much. If you have any question, I will be happy to answer. Thank you.
Yeah. Sir, thank you so much, sir. Everyone is praising. I'm getting calls. I'm getting like messages from everyone that it was such an informative lecture, sir. Everyone will be watching all your. They'll now just go through all the channels. Thank you for sharing with us. And I think that slide which covered that lineage of your complete chemical biology of the people who had worked with you, and you have done your PhD and you could get down up to that was one of the kind of slides I've ever seen, and we are so fortunate to hear you, sir. And I'll take few questions and then I'll request Dr. Nutan Kaushik ma'am also to share her views. She has joined us in the panel. Kapil Shakla sir had also joined us in the panel, but he was facing some audio problem. So because it's a new platform, go to webinar. And sir, there are I'll take two questions, and there is it is full of everyone is just writing very enriching lecture, sir. Thank you, sir, for this interesting and informative talk. Thank you so much, sir, and everyone is thanking you, sir. So the first question is like, sir, why does parallel magnetic fields correspond to lower energy? This is from Ajanta Chatterjee.
What is the question?
Why does parallel magnetic field correspond to lower energy?
Okay, parallel magnetic field is like this actually. You have a nucleus. You have a nucleus and it is surrounded by the electron like this. Okay,
Yes,
and when the electron density around the nucleus is higher, you have an applied magnetic field here. So it means it will shield the applied magnetic field. This is why I said
field.
the induced magnetic field versus applied magnetic field. To explain that, it requires more of physical way of explaining things. And that is why I always prefer to teach the student in terms of the electron density, which people can easily visualize. It is because
Yes,
of the
sir.
electron density.
Electron density. And sir, one more question is from Dr. Shalini Jaiswal. She's asking, could NMR spectroscopy distinguish COVID-19 patients?
Difficult to say. Difficult to say. As of today, no. NMR is used in MRI on the same principle actually. The
Yes,
hydrated form, how much is there. So in the COVID, it is not used in
yes,
any
sir.
other disease. It has not been used.
And I'll take one last question, sir. How population difference affects resolution?
Yes. What happens? What happens? The population difference is about 10 to the power minus 6 or 7 only. So it means if you have a lower energy level to higher energy level like this, okay, the difference between
Yes,
this population to this population is really, really small. So what happens when the population of the excited state and the ground state becomes same, what we
yes.
call a saturation, you won't be able to see the NMR signal.
Okay,
Okay,
sir.
so to increase that, if you increase this gap like this, so there will be a population gap
Hmm.
now. Then that population gap gives you the NMR signal.
Okay, sir. Okay, sir. Sir, now I just request Nutan Kaushik ma'am also. She is she's one of our panelists, and I had introduced her in the beginning. So, ma'am, I request you to kindly share your questions and views on this webinar, ma'am. Hello, Nutan, ma'am. I'll just see because Nutan, ma'am, are you able to hear us, ma'am? We are
Ma'am,
not
please
able.
check your mic. You are
Nutan, ma'am.
muted, ma'am.
Yeah, ma'am. It's muted, ma'am.
Now it's okay. Ma'am. Please say something. Just unmute your again.
Unmute again, ma'am. Yeah.
Yes. Yes, speak something, ma'am. Ma'am, say something. No, ma'am, your audio is not coming. Please eject your headphone, ma'am. I think there is some issue on.
Without headphone, ma'am, if you want to speak.
Ma'am, now speak, ma'am.
Um,
No, ma'am, your audio is not coming.
Okay. So, sir, there is like from Dr. Hema Bhandari has also said, excellent webinar, sir. I have learned a lot. Thank you for conducting such an informative lecture. Dr. Sarla Kumari, thank you so much, sir. So, I just wanted to tell you all the DU colleges have also joined us. There were,
How many people were there?
sir, there are more than like the registration was more than 300 plus. So
Okay.
we have like a lot of audience, but the exact numbers I'll be getting it later on. So because yeah, sir, but because ma'am is not audible right now, this is a new platform. So I really thank you, sir, for your time. On behalf of our Honorable Founder President, sir, Dr. Ashok K. Chauhan, Chancellor, sir, Dr. Atul Chauhan, sir, and Vice Chancellor, ma'am, Dr. Balvinder Shukla, ma'am, and all the scientific fraternity and all the scientists, students who have joined from India and all over the world today. I thank you for joining us and being a part of this webinar. And most importantly, we all thank Rawat sir for his valuable time and sharing such a wonderful session, sir. We have learned a lot and we will be watching over all the YouTubes and we'll learn a lot, sir. So have a good day, sir. Thank you so much, sir.
Thank you. Thanks.
Thank Thank you, sir. Thank you so much. So we can all leave. Thank you, everyone. Thank you.